For our project, we decided to focus on magnets, specifically magnets in vehicles.
Magnets! What? Oh my god.
Starting off with some brief history, magnets were first discovered around 600 BCE by a philosopher named Thales. He documented magnetic forces between lodestones. After that, we saw some advancement with William Gilbert, who discovered that the Earth itself was a ginormous magnet.
Gilly?
He was the first to use the scientific method to investigate magnetism. Next, we have artificial magnets when they were created, which was around 1730 by Servington Savory.
Sir!
He bound magnetic steel needles together to create stronger forces, and he discovered that magnetic force persisted over time. We see that electricity and magnetism coincide with each other pretty well. Francois Arago found electrified wires could magnetize nearby iron. And then William Sturgeon developed the first horseshoe-shaped electromagnet. It could lift very heavy objects when charged, and it would release them when the current stopped. And then the Maxwell equations, we learned this. James Clerk Maxwell revolutionized physics.
Physics 2?
By finding a way to calculate all the electrical and magnetic effects of electromagnetism. Alright, so General Motors and magnets. Little history about that. In 1982, the alloy for neodymium magnets was discovered, which is a neodymium iron boron alloy. This alloy has the abbreviated designation, I don't know how to say, The composition was developed in 1982 by the research department of the General Motors Company and by the Japanese solid-state physicist Masato Sagawa.
GM?
So, in traditional combustion vehicles, GM used magnets in the anti-lock braking system, ABS, locking mechanisms, seatbelt indicators, and they were essential for various automotive sensors, like the tire pressure monitoring sensor, door closure detection, and other safety features. GM's first electric vehicle, the EV1, was mass-produced in 1990, and it was the first electric vehicle made by any automaker. It featured innovative regenerative braking system, and it converted kinetic energy to electrical energy through magnetic induction. Now on to a practical application demonstration.
My name is Jake Schulze, and for my portion of the project, I will be showing how magnets are used in your daily driver. And everyone experiences these every single time they drive their car, and they're extremely helpful with safety features and data analysis and just running the car. So for today, I'll be using my personal car, my WRX, to show where they're all used. Now, for the first example, everyone uses a seatbelt whenever they want to drive a car. And I'm sure everyone has at least tried to drive off, or maybe if they forgot something and had to get out, and they would sit back in the car, and it might start giving a loud tone, or give you a little notification that, hey, your seatbelt is not on. And the reason why that works is you put your seatbelt back on, the metal tip goes into the latch, and it's off. It's a little bit more complicated than that. So inside the latch is something called a reed switch, which uses ferromagnetic sensors. So when the buckle goes in, it creates a electromagnetic field, which then when it's plugged in, it closes the reed circuit, which then sends the current through, telling the data analysis system that your seatbelt is on, which then transfers to the car, and it will stop beeping and will tell you that the driver is safe. Another example is your doors. whenever they're open, you also get another pop on the dash that says, hey, your door's open, whether it's this or your trunk or somewhere else. When this is closed, this also, the light also goes away. And the process of this is nearly identical to with the seat. So inside the door, there's also another reed circuit. So whenever it's closed, the magnetic field flows through, whenever it is closed, the circuit will then have a current flowing through, which will then go to the car, telling the dash and all the data systems that, okay, you're safe, doors closed, all good to go. Finally, it's a little tricky to see, but under here is the alternator. The alternator, any electrical systems that are running through the car go through the alternator. So the battery starts the car, but the alternator keeps it going until the battery doesn't die. Inside are spinning spinning magnets that push against almost as a plate, keeping a EMF and making sure that the system runs okay, generating electricity for the rest of the car. Another example that's a little bit harder to access is in the wheel, you have something called an ABS sensor, which is the anti-brake lock system. That sends EMF waves to the wheel, or it gets collected from the wheel, which then are read by the EMF sensor, which are then received through here, so the driver has feedback on whether their brakes are working or not, and they won't lock up. Meaning of lock up means if you brake and your wheel actually just doesn't move, you might see some smoke. But yeah, those are some examples of magnets in your daily driver. Without magnets, we'd be driving a lot less safe. So yeah, handing out to Carson now.
That was the practical application demonstration, and now I'm going to talk about electric vehicle motors and some of the future that we can see with magnets in vehicles. So, magnets in electric vehicle motors help convert electricity into torque, which drives the vehicle. The highest performing electric vehicle motors today all use neodymium iron boron magnets, which Caleb talked about a little earlier. There are essentially 4 magnets in an electric motor, 2 on the spinning shaft, and 2 on opposite sides of the outer casing. They use a push and pull mechanism to rotate the shaft magnets, and it's basically, they rotate, and as they get closer to one, the polarity of the shaft switches, so then it pushes towards the other until it gets close enough, and then it just goes back and forth. So the most used motor in electric vehicles is the permanent magnet motor. And the magnets within generate a magnetic field which causes the rotor to rotate. And yeah, the field within is a constant, meaning that the speed of the rotor is related to the magnitude of the magnetic field that it is producing. What makes them so special is that they don't rely on the electrical current that most motors do, and most motors use that electrical current to create a magnetic field, which these already have a magnetic field created. You can find these motors in alternators, power tools, and electric vehicles such as like Teslas.
Musk!
So, for the future of magnets in cars, magnetic levitation, also abbreviated as like maglev, uses powerful magnets to lift and propel vehicles without touching the ground. It's like a future thing that has been being worked on for the past couple years. Newer magnets are being used, and they're superconducting and can generate magnetic fields up to 10 times stronger than what they were using previously. And that is now able to hold trains and cars in the air. Magnetic fields interact with simple metallic loops through the walls and the ground that these cars are being driven through, and this creates an electric current and another magnetic field. So basically there's 3 different loops that these cars and trains revolve around, and one is to make the car hover, Another is to make it stable, and the last one is to propel it forward. So the track itself is a magnet, and the car also is magnets. And based on like three different like loops that these magnets are like pushing and pulling against each other, it causes these things to happen. And then these are, we're excited. Thank you.